The stateless architecture pattern is probably one of the most important patterns in software architecture. In fact, if I had to single out one pattern as the one you must implement, it probably will be the stateless pattern. So what is this stateless thing? In stateless architecture, the application state is stored in only two places, the data store and the user interface, if there is any. No state is stored in the application code. Now, if you are not sure what state is, you can think of it simply as the application's data, either temporary or persistent. To make it clearer, let's use an example. In our example, our application has a login mechanism similar to almost any other application out there. The application consists of user interface, a login service, and a database. The user enters his username and password. They are sent to the login service, which checks with the database whether such a user exists. If so, the user details are retrieved from the database and are stored in a variable in the service so that in future requests the application will be able to identify him. In this example, the state, which in this case is the user details, is stored in the application code, thus making it stateful rather than stateless. Now, what is the problem with it? Why is stateful code considered a bad thing? To understand that, we should discuss two other concepts that we already mentioned before but are worth mentioning again. The first is scalability. As you probably remember, scalability is a capability of the system to grow and shrink as needed. When there is a peak in the load of the system, a scalable system can simply add more resources, and when not needed anymore, these resources are removed, all this without any interruption to the system's activity. As you probably remember, we discussed the difference between scale up and scale out and concluded that scaling out is almost always preferred over scaling up. The second concept is redundancy. Redundancy means that when a resource of the system stops functioning, either because of a system problem or because of a hardware glitch, the system will continue functioning using additional identical resources it has and can also perform automatic scaling to other resources instead of the malfunctioning resource. For example, with a system with more than one server, if one of our servers experiences electricity problems and shuts down, the system will be able to continue functioning with additional servers and perhaps even create a new server and add it to the existing ones. Those two concepts are the cornerstone of any good architecture and must be taken into account when designing the system. Now, to implement these concepts, our architecture must look like this. As you can see, we have more than one service instance. The exact number doesn't really matter, but the best practice is to use at least 3 instances. In front of the servers, there is a load balancer. The load balancer is an appliance or a software that has 2 roles in the architecture. First, it distributes the load between the servers. If one of the servers is very busy, the load balancer will route requests to another server and will make sure no server will crash under the load. This capability supports the scalability we need. Using the load balancer, we can add more servers as needed and just notify the load balancer of the new servers. Second, it checks for the status of the servers and knows to stop routing requests to malfunctioning ones. The way it works is that the load balancer sends periodically a request to each server called isAliveRequest and expects to get a response with a positive answer. Any other response or no response at all will indicate there is a problem with the server and the load balancer will stop routing requests to this server. As you can see, this role supports the redundancy we talked about. The load balancer allows the application to continue working even if one or more of the servers are down. This is exactly what we want to achieve with redundancy. There are a lot of load balancing algorithms, but the basics are always the same. Distribute the load and stop routing to non-functioning servers. Okay, so we have learned about scalability, redundancy, and load balancers. But what does it have to do with stateless architecture? Well, actually, these are tied to each other. A stateful, non-stateless application will have a very hard time with scalability and redundancy. Let's see why. Remember the login scenario? Let's look at it again, but now from a point of view of a full-blown system with multiple servers and a load balancer. So the user logs in. The request containing the username and password is sent and reaches the load balancer, which routes it to server number 1. The server performs the login process and keeps a variable for verifying the user in future requests. Now, the user performs another request. Let's say he wants to add item to a shopping cart. The request containing the item to be added is sent, reaches to the load balancer, but this time the load balancer routes it to server number 2. Now, look what happens. The request arrives at server number 2, but this server has no idea who the user is. The data containing the user data is on server number 1. What will happen in this case is that the user will get an error message saying he should log into the system, which will leave him confused since he just now did exactly that. And the one thing you don't want to do to your users is to confuse them. The reason for that error is that the code is stateful. The application code contains state or data, which is the user details in this case. Additional resources or servers that are used for scalability and redundancy simply have no idea about the data in the code and behaves as if it does not exist. The statefulness of the code made the application harder to scale and damaged the user experience. Now, what would have happened in a stateless architecture? In this case, the user data will be saved in some kind of data store. It could be a relational database, a NoSQL database, a distributed cache, anything that can be accessed from all the servers. Then, when the request arrives to the server, it queries the data store for the user details and immediately knows exactly who the user is, regardless of the server that performs the actual login. Note that this goes the same for redundancy. If the server that performed the login was shut down for whatever reason, subsequent requests won't be routed to it, and again the server accepting the request will have no idea who the user is. So this is the reason why stateless architecture is so important. It fully supports scalability and redundancy, which make your application much more reliable. To conclude, always make your architecture stateless. There are almost no scenarios which justifies stateful architecture, and you probably will never encounter them. This is the best way to support scalability and redundancy in your system, and you should definitely use it.